where an evil super genius finds a way to suck all the oxygen out of the air, then buries it in the ground. Sounds like the stuff of comic books. Well, yes, if we are talking about oxygen. What scientists are working on a way to do just that with carbon dioxide. Why capture carbon dioxide from the air to combat global warming and climate change? Carbon dioxide is a natural gas that allows sunlight to reach the earth but also prevents some of the sun's heat from radiating back into space, thus warming the planet. Scientists call this warming and the greenhouse effect. When this effect occurs naturally, it warms the earth enough to sustain life. In fact, we had no greenhouse effect. The planet's average surface temperature would be just 0 degree Fahrenheit. Lang, sure, the sky might be great, but we had all be too dead to enjoy it. Yes, carbon dioxide and the greenhouse effect are necessary for life on Earth to survive, but human invention designed to burn fossil fuels, such as power plants and transportation vehicles, are releasing extra carbon dioxide in huge quantities, and that's not good. Decade of 2011 through 2020 was the warmest one on record. World Meteorological Organization, according to the World Meteorological Organization, since the late 1800s, our planet's average temperature has climbed by roughly 2.12 degrees Fahrenheit, according to NASA. As a result, ice at both poles is melting, so levels are rising, animals are changing their migration patterns, and many places have seen an uptick in extreme weather events. So, what's the main driving forces behind the warming trend? Unfortunately, humans between 1970 and 2004, carbon dioxide emissions rose by 90%, and in 2019, the global average concentration of carbon dioxide within the Earth's atmosphere was higher than it had been at any point in the previous 8 lakh years, Lindsay. Recently, the United Nations Economic Commission for Europe called for the wide-scale deployment of carbon capture technology. Carbon capture involves trapping the carbon dioxide at its emission source, transporting it to a storage location, usually deep underground, and isolating it. This means we could potentially block excess carbon dioxide from entering the atmosphere. Trapping carbon dioxide, carbon capture technology. There are three main steps to carbon capture and storage: trapping and separating them from other gases, transporting this captured carbon dioxide to a storage location, storing carbon dioxide far away from the atmosphere, underground, or deep in the ocean. Let's take a more detailed look at the trapping and separation process. Carbon is taken from the power plant sources in three basic ways: post combustion, pre combustion, and oxy fuel combustion. A fossil fuel power plant generates power by burning fossil fuels, coal, oil, or natural gas, which generates heat that turns into steam. That steam turns a turbine connected to an electricity generator. Another word for the burning process is combustion. With post combustion carbon capture, the carbon dioxide is grabbed after the fossil fuel is burned. The burning of fossil fuels produces something called flue gases, which include carbon dioxide, water vapor, nitrogen, and sulfur dioxide. In post combustion process, carbon dioxide is separated and captured from the flue gases that results from the combustion of fossil fuels. This process is the most commonly used technique in carbon capture technology. It is convenient strategy because it can be deployed at both new and pre-existing coal-fired power plants. However, there are some drawbacks. In order to work post-combustion, carbon capture requires some physically large equipment and it can make turbines less efficient. With pre-combustion carbon capture, carbon is trapped and removed from fossil fuels before the combustion process ends. Fuel, coal, oil, and natural gas is heated in steam and oxygen, resulting in a synthesis gas or syngas. The, the gas mostly contains carbon dioxide, hydrogen, and carbon monoxide. Later, a separate reaction converts water into hydrogen. While that's going on, some of the carbon monoxide is transferred into carbon dioxide. The end result is a gas mixture loaded with hydrogen and carbon dioxide. It is easy to isolate, capture, and sequester the carbon dioxide from that mix. Meanwhile, engineers can use the hydrogen for further energy production processes. Pre-combustion carbon capture is usually more efficient than the post-combustion strategy. However, the equipment comes with a higher price tag. Besides, older power plants tend to be less suited for this technique than some new ones. With oxy-fuel combustion carbon capture, the power plant burns fossil fuels but not in ordinary air. Instead, the fuels are burned in a gas mixture containing lots and lots of pure oxygen. This results in a flue gas whose two main components are carbon dioxide and water. Afterward, it is possible to separate out the carbon dioxide by compressing and cooling the water. Certain aspects of oxy-fuel combustion carbon capture are inexpensive, but the process has a high cost overall. Pure oxygen is not cheap. Also, there are some concern about its applicability. A 2020 review published in the journal Catalyst argued that the relevant technology needs to be proved for large-scale operations. On the positive side, oxy-fuel combustion capture can be used at both old and new coal-burning power plants, transporting carbon dioxide. After carbon dioxide is captured, the next step is transporting it to a storage site. The usual method of transporting carbon dioxide is through a pipeline. Pipelines have been in use for decades and large volumes of gases, oil and water flow through pipelines every day. Carbon dioxide pipelines are an existing part of the infrastructure in the US and many other countries. In fact, there are now more than 4,039 miles of carbon dioxide pipeline distributed across Africa, Australia, the Middle East and North America. Most were created for a process called enhanced oil recovery, but some are connected to CCS projects. You can put a pipeline just about anywhere, including underground or underwater. They can be found running through such diverse environments such as desert, farmland, mountain ranges, and oceans. Pipelines may be connected to processing plants or power plants that rely on fossil fuels as well as natural sources of carbon dioxide. The purity of lines carbon dioxide supply may be affected by the kinds of technology used at its sources. In some cases, the carbon dioxide might travel as far as it can in the pipe, then transition to a tanker, truck, tanker ship, or pressurized cylinders to finish its journey. Note that there is an asphyxiation and risk of a massive amount of carbon dioxide escapes into the atmosphere. As with tanks and transport natural gas, other hazards, material good construction is key. That and good driving. Getting back to pipeline, they can transport carbon dioxide in three states: gaseous, liquid, and solid. Solid carbon dioxide is commonly known as dry ice, and it is not cost effective to transport carbon dioxide as a solid. Pipeline commonly transport carbon dioxide in its gaseous state. Said gas needs to be compressed it's now before it's moved from point A to point B. According to the National Energy Technology Laboratory, the ideal pressure range is about 1500 to 2200 psi. Engineers must be on guard against impurities in the carbon dioxide stream like hydrogen sulfide and water. The latter has been known to corrode pipelines, but that's just the tip of the iceberg. Under high pressure and low temperature, the water in these pipes may form natural gas hydrates, solid crystals that can be clog up your lines. Scientists are still devising ways to handle such impurities. In the world of construction, safety is a top priority. If a pipe ruptures near a populated area, the sudden release of carbon dioxide gas in large quantities could have serious repercussions for both the public health and the environment. To keep industrial digging equipment from accidentally striking the pipes, planner can bury them deep underground also when possible. Laying pipeline down far away from cities, towns, and the like might be advisable. DNV, a prominent risk management and quality assurance company based in Norway, released new safety procedures for carbon dioxide transport pipelines in 2021. Meanwhile, the United Kingdom Health and Safety Executive now has an extensive list of guidelines covering everything from corrosion to land uses. Pipeline cost fluctuate depending upon the route of pipeline through heavily congested areas, mountains, and offshore. The quality of the material, the equipment involved, how much labor is required, and other expenses. Creatures of carbon. Carbon atoms represent around 12% of all the atoms in your body. To put that in perspective, a 176-pound person contains roughly 31.7 pounds of carbon. We think you will agree that a significant figure of all the elements required to make a human body, only oxygen accounts for more body mass. Furthermore, over 99 out of every 100 atoms found in our bodies are oxygen, carbon, hydrogen, or nitrogen atoms. Carbon storage already discussed, and you can see in the figure how carbon capture and storage works, the Royal Society of Chemistry. After we collect the transport all the carbon dioxide, we are going to need somewhere to put it, but where? In some sort of giant storage unit, a huge tank out in the desert. Will we need more landfills to hold our carbon dioxide waste? Don't worry, the answer to all those questions is no. There are a few places we are found to store carbon dioxide, including several underground. In fact, there is research that suggests the United States alone has enough subsurface space to potentially hold 1.8 trillion tons, means 1.71 trillion metric tons of carbon dioxide in deep aquifer, permeable rocks, and other such places. Let's talk about the logistic of underground storage. Deep underground carbon dioxide can be kept at pressure of over 1057 psi and at temperature above 88 degree Fahrenheit. When those specific conditions are met, carbon dioxide becomes supercritical. In that state, carbon dioxide takes on properties normally associated with both gases and liquids. Supercritical carbon dioxide has a low viscosity, just like a gas, but at the same time, it's also got the high density of a liquid because it can seep into the spaces in porous rocks. A great amount of carbon dioxide can be stored in a relatively small area. Oil and gas reservoirs are well suited to store carbon dioxide as they consist of layers of porous rock formation that have trapped oil and gas for years. Carbon dioxide is artificially injected into underground rock formation below the Earth's surface. These natural reservoirs have overlying rocks that form a shield keeping the gas contained. There can be risk to underground storage, though, and we will discuss those a bit later. Basaltic rock formation also make attractive carbon dioxide storage spots. Volcanic in origin, basalt is one of the most common types of rock in the Earth's crust. Researchers have found that when carbon dioxide reacts with the magnesium and calcium basalt naturally contains, it can be transformed into solid minerals, specifically dolomite, calcite, and magnesite. Then we have coal deposits, sometimes the ones that have been written off as unminerable, can hold very large quantities of captured carbon dioxide. It's possible to store the gas at lower pressure and thereby save money. Thereby save money. In addition to underground storage, we are also looking at the ocean for permanent carbon dioxide storage. Historically, there has been a lot of discussion about the potentially dumping carbon dioxide straight into the ocean at depths greater than 9,842 feet, that far below the surface. Carbon dioxide is actually denser than water, so hopefully the dumped carbon dioxide would be trapped in place for some time. Ocean carbon storage is largely untested, and there are many concerns about the safety of marine life and the possibility that the carbon dioxide would eventually make its way back into the environment. Next, we will look at some of these concerns in more detail and find out if carbon capture and storage is a variable solution for our future. In enlisting the seas, one hypothetical method of carbon dioxide removal was recently proposed by scientists at the University of California, Los Angeles. The plan would involve extracting carbon dioxide from seawater and artificially converting it into limestone and magnesium for storage. The water in our ocean naturally contains around 150 times as much carbon dioxide as Earth's atmosphere. By removing existing carbon dioxide, we could theoretically coax seawater into pulling more of this greenhouse gas out of our atmosphere, called single-step carbon sequestration and storage, or SCS. The process would most likely require a huge financial investment, about $1 trillion. Carbon storage concern. The Petra Nova facility, a coal-fired power plant located near Houston, Texas, is the only carbon capture and storage facility in the United States. It reportedly captures and repurposes more than 90% of its own carbon dioxide emission. Although carbon capture and storage may seem like a miracle solution, it's not without concern or controversy. To begin, it's important to remember that carbon capture and storage is not a license to continue emitting carbon dioxide into the atmosphere. Whatever the future holds for CCS, other emission reduction efforts will still be necessary. However, CCS provides a way to clean up some of our existing power plants. According to a 2020 report from the Global CCS Institute, there are now 65 there are now 65 commercial CCS facilities in various stages of development globally. Yet some critics worry about the economics of CCS. Electric cars and solar panels are commodities that can be marketed and sold to individuals and private organizations. But in contrast, finding ways to monetize captured carbon dioxide has proven difficult. Another drawback, current CCS technologies actually require a lot of energy to implement and run. Besides, they depend on water and lots of it for cooling and processing purposes. Given this need for hydroxide, there have been debates over how CCS might or might not contribute to water scarcity. Given this need for water, there have been debates over how CCS might or might not contribute to water scarcity. In 2020, a team led by Lorenzo Rosa at the University of California, Berkeley simulated the retrofitting effects of retrofitting every large coal-fired power plant in the world with 4 different kinds of CCS technology. To quote their paper, which the journal Nature Sustainability published May 4, 2020, certain geography lack sufficient water resources to meet the additional water demands of CCS technology. And this is just one of the environmental concerns folk have raised about carbon capture and storage. What happens if the carbon dioxide leaks out underground? It's hard to predict what the distant future holds for carbon dioxide. We have already trapped below the Earth's surface. Implementing good regulation and choosing quality storage sites might make an enormous difference down the road. There are few potential ways for recaptured carbon dioxide to leak to the surface. Ironically, the balls built to inject it underground in the first place could become a possible escape route later on. So could abundant oil and gas wells or natural faults. One 2018 projection claims leaks are unlikely if realistically well-regulated storage is put into effect. This contradicts some earlier research on the matter. Some opponents of CCS believe that, viable or not, the focus is all wrong. They say we should be focusing on ways to wean ourselves of fossil fuels, but CCS prolongs the lives of power plants that rely on them. On the other side of the divide, CCS supporters believe renewable are only part of the solution. In this view, we will probably need to combine these with carbon capture tech in order to have any serious hope of thwarting catastrophic climate change. There are still many questions about the role carbon capture and storage will ultimately play in helping us elevate the greenhouse effect and fight climate change. But one thing's for certain, carbon dioxide emissions are a worldwide problem. Trees won't save us. Trees are definitely our allies in the crusade against global warming and climate change. Photosynthesis allows them to absorb and store carbon dioxide, so the plants act a bit like all natural CCS devices. Unfortunately, scientists say there is no way to plant enough trees to contract all the excess carbon dioxide we have pumped into our atmosphere by burning fossil fuels. Beside older forests populated by a variety of tree species, are better at locking carbon dioxide away than younger, more homogeneous ones. Please, thank you. Please subscribe, like, and comment.